So today, we're going to talk about relating delta U and delta H. And that review I gave you is associated with it. You don't have to formally read all of that review, but it's pretty interesting. It's about superconductors. So one of the authors on that is my advisor's postdoc advisor, Roald Hoffman. Does anybody know who Roald Hoffman is? He's a professor of chemistry, I think emeritus now at Cornell University. He won the Nobel Prize in the 80s for explaining the Hoffman-Woodward rules through computational means. There's something called semi-empirical Huckel theory. But you guys know about like Diels-Alder reactions, right? How they have to be symmetry adapted, blah, 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 all that junk. He helped develop those rules, and it was from like a computational portion that he started and got to explain those rules, so it's pretty cool. He then later started to focus on meshing chemistry and physics together, and one of those things are superconductors. Does anybody know what a superconductor is? Okay. It's a conductor that has no resistance. The beauty of that is it can transmit energy basically freely. Why would that be a good thing in today's world? Why would we need it? So, literally millions upon billions of your taxpayer dollars go towards finding superconductors. What do you think,
It's
Shannon?
like a renewable energy source that wouldn't run out.
Yeah. So if you think about like, okay, what's the problem with solar panels? Like we could pick a spot in Nevada that completely sucks and it's just desert and nothing lives there. Hell, Death Valley, nothing's alive in Death Valley. Hence its name.
Storing the energy.
Yeah. Storing the energy is tough. We're transmitting the energy is an even bigger problem. So another big thing is with our NMR or MRIs. Do you know what's the downside to having those instruments? They have a superconductor actually on the inside of them. Does anybody know what we have to do constantly to that instrument though? It's okay. So what do we have to constantly do? Or, like, do you guys know about MRIs at all, or not really? How many people have ever had an MRI? Okay. Can you tell us a little bit about having an MRI?
It's like a big magnet that like spins.
Yeah. And that big magnet is actually a superconducting magnet. You need really cold temperatures right now to get a superconductor. So our magnet, the NMR in the other room, which is the exact same thing as an MRI. You need liquid helium, and you need liquid nitrogen. So what you have is you have a set of coils, and in that, they're submerged in liquid helium, which is around 7K, and then on the outside of that, you have liquid nitrogen, which is at 77 Kelvin. We have to fill liquid nitrogen every week. Helium happens once every 3 months. During COVID, when all these shutdowns and things were happening, liquid helium, it became a priority only for MRIs, for imaging, for health purposes. We could continue to get it because we were seeing, we had a good source of getting it. This costs us $3 grand to get every 3 months, so about, $9,000 to $12,000 every year, and then this is about $200 every other week. Liquid helium, or helium, is one of the scarcest resources we have on this planet because it can escape the atmosphere. So once we use the helium, it's gone. Now, if you're thinking of all the imaging with MRIs, you need the liquid helium to keep the magnet cool, keep it superconducting, to get good signals, which means a lot of resources. So what you were saying for sustainability, Shannon, yeah, we got a superconductor that would be good. One, we could transmit energy, and then the other aspect of it is we would, for our imaging, we wouldn't have to submerge everything in liquid helium, which costs a ton of money. So, we're on the search of that. So that's what that review is about. What's the definition of enthalpy again? How did we define it? And we're going to connect this to that superconductor idea or other solids in a little bit. So what's enthalpy defined as? Yeah. Okay. So my question for you is when does delta H equal delta U? Looking at this equation.
When pressure and volume are constant.
Yes. So when delta P are small or constant, right? Okay, sort of dealing with the daily problem, bless you, that we had earlier today. That you had to think about a little bit with that change in volume. Which phases? The delta H and delta U have the greatest difference. Ambient temperature and pressure. What do I mean by ambient temperature and pressure? Does anybody know what that means? Just means room temperature and pressure, basically. Ones that we can access pretty easily. Okay, so for those phases, or if we think about the three major phases, what do we got?
Solid,
Yep,
liquid,
yep,
gas.
yep. There's a bunch of other ones, but we're not going to worry about those ones. Those are for the real nerds. We're the cool nerds. All right, so here, when we're talking about delta H and delta U and differences, what phase is going to be impacted most?
Gas.
Yeah. Why?
Like we saw the daily problem, like when you vaporize something and you go from like liquid to gas, the volume like increases dramatically.
Yeah, exactly. So you guys saw like about with approximately 1 milliliter of water, if you take that 1 milliliter of water and turn it into a gas at 100 degrees C, how much volume did it occupy? It went from like 1 times 10 to the minus third liters to what? Like, let's stare at somebody's thing. Like 1.7, almost 2 liters. So it expands a lot, right? What about liquids? What about solids? Do they change much in comparison to that guy? No, this one is the one where they have the major impact. So we're going to try and improve that. We're going to look at a change in a mineral. How many people like minerals and rocks and stuff? I know you two are in earth science right now. So what's your favorite mineral, Lily?
I don't know. I like calcite.
You like calcite?
Yeah.
Yeah, that's what we're talking about right now. What about you, Will? Do you have a favorite mineral right now?
Not really.
Okay. I like bismuth a lot because it does a lot of networking. Anybody else have a favorite mineral? My daughter's is peacock ore right now. She absolutely loves it. I'm not one of those crystal people, so that's always very irritating too. I go to like these gem shows and stuff, and they're like crystal people that are like, man, it changes your mood, and I'm like, I like the tessellation. So you get these like, and there's always like you have either the hippies or like the super nerds, and then they both have people who do not have hygiene in either of those. It's pretty gnarly. Okay, so we're gonna look at the change in internal energy when, have you guys ever talked about polymorphs before, or no? It's more of a crystal thing. So polymorphs, you can have different crystals but the same molecular formula. It's just a different arrangement of those crystals. So it's related to like isomers for molecules in a way. Different arrangement, and you have different properties. So what we're going to talk about is when we have calcium carbonate as calcite converts to another form, argonite. Oh, actually, sorry, we're not looking for the change in internal energy, we're looking for the change in enthalpy. So we're told that delta U is that. We want to calculate the difference in the molar internal energy and molar enthalpy. Given the density the polymorphs are, we've got 2.71 grams centimeter cubed for calcite, 2.93 grams and we're going to do that at two different pressures. A, 1 bar, and B, 100 gigapascals. So really, really high pressure. Can I steal this for a second? Okay. So 100 gigapascals, if you look on here, it shows you kind of like a scale associated where, like what happens as you increase the pressure. So for example, at about 60 gigapascals, you get symmetric ice. It's called ice X. So that's where you have a network of water molecules, and it looks like an X. The H's and the O's are that distance away. Oxygen becomes metallic at a little bit less than this pressure. So that's kind of weird too. Suddenly it's a metal when it's meant to be a gas and an insulator. So that's a really, really high pressure. If you look, like what's the internal pressure of the Earth's core that they approximate on there? Yeah, 380. So much higher pressure than what we're seeing. So we're going to look at, you know, normal pressure, ambient pressure, and then we're going to look at crazy high pressure. Before we do that though, what are we looking for in the problem? Yeah. So we got to calculate molar internal energy, molar energy. What information are we going to utilize?
The density.
Yep, definitely the densities. What else?
Engine, molar, internal.
Yeah. Anything else?
Pressure.
Yeah, those pressures. Okay, first let's figure out what we mean by molar internal energy and molar enthalpy. So we have change in delta U, we'll call it U sub m. What's that going to be equal to? Or let's relate it back, we know molar volume, right? What was molar volume? Yep, V over N. Okay, so what will delta U sub m be? Delta what?
Delta.
Yep. In this case, we're just gonna leave it as N. We're gonna say the moles aren't changing. Then we got delta H sub M. What's that gonna be equal to?
Delta H over M.
Yep. Okay. What are we looking for in the problem though? Yeah. That's what we're trying to find. Okay, before we do that, let's find this guy. When we do that, we'll be able to figure out, we'll see that this is actually gonna fall out of there, okay? All right, delta H sub M. Delta is always what minus what? Yep. Okay, so what is our final state? What is our initial state?
Is the final state the argonite?
Yes.
And the initial is the calcium carbonate.
Yep. So our final state, let's go for argonites. And then we'll look at calcite. Okay. Oh, I'm sorry, there should be a sub M here. How did we define enthalpy again?
U plus P.
Yep, U plus PV. Okay. So here, what we can do is we can solve in for these guys, right? So H sub M of argonite, what will that become if we want to use this identity? UM of what? Yeah. We'll just shorten that to A for now so we don't have to write that a million times over and over. What else do we got here? Yep, we got P. So the nice thing is we're talking about it at isobaric conditions, so we're gonna have the same P for this system right now, right? But what are we gonna multiply this by? The M of our argonite, right? Okay, now the other portion of this. Minus, what are we gonna subtract off this thing? Yep. UM, and then we'll just shorten that to a C, minus P, and then what here? Yeah. Okay, we can make this a little bit simpler, right? What would you suggest to do? Yeah, we can take out the P. anyone see any other ways we can maybe get a bit closer to the question we're trying to answer? So, yeah, what do you
Make
think?
that delta UM.
Yeah, this is delta UM. That makes our lives easier, so now we don't even actually have to plug anything in here, we can just shuffle it to the other side. Am I okay to erase this bit over here? So now, get delta HM is equal to delta QM plus P aragonite minus V calcite. What do you suggest to do now?
Subtract it. The delta.
Yeah, take that delta U away. All right. What do we know in here? What don't we know in here?
We know pressure.
Yep. We know pressure. Do we know those molar volumes? What are we given? Density. Let's try and stare at this and see if we can't find a molar volume here. Or a density from this molar volume. Okay. VM is defined as what again?
Volume over moles.
If I wanted to get moles, how do you always calculate moles? So let's make it a little bit different. Let's say I have like 2 grams of oxygen. Denominator, what goes there? Yep, what goes up top? Yeah. And then mass is what, 31.998. Okay, what is this thing?
The formula.
Yeah, formula mass, molecular weight. So we have a mass, and what are we actually dividing by? Yeah, the molar mass, and what does that get us? Okay, so if we wanted to make a little simple formula here, what's going up top? Yeah. And then what's going in the bottom? Yeah. We're gonna give that the symbol fancy M. That's molar mass. And then what's the pink one again? Yeah, just whatever mass we're dealing with. Okay. How about we take this, sub that in there, so we get B divided by what?
M over fancy.
Yeah, M over fancy M. What are we working with again? Or what information were we told? Density, okay. I'm gonna give it the symbol rho. Density is defined as what over what? Okay. Can we see a density anywhere in here? Where do you see a density? Where do we spot that? Yeah, that's a sorry.
B over M would be 1 over density.
Yeah. So now we get 1 over rho divided by that fancy M What's that gonna work out to be?
Fancy on the.
Yep. Anc over rho. Ha! Now we've got what we need to plug in here. Push that thing in there, we have something, so we got P times what? Rho of what? Argonite? Minus what? Okay, should I have a sub A and a sub C here for my molecular masses? I see a head shake, no. Why not? Yeah, they're the same, right? It's just calcium carbonate, it's just in different forms. So we can simplify that even further. P times fancium. 1 over those densities. Okay. We can plug in everything associated with this. Does anybody want to see me actually do that, cancel the units out or anything? Okay, so what was our first pressure at A? Yep. 1 bar, if you calculate this delta HM minus delta UN, and you plug in all of that junk, make sure the units cancel out. The value you get is 0.277 joules per mole. Is that a lot of energy? No. If you think about raising 1 gram of water 1 degrees C, which is around like what, 4.1 kilojoules per mole, that's tiny. It's not enough even, I think, for your fingers to register that there's been a heat exchange. If you do it at, what's our other pressure? Is it 100 gigapascals? You do it then, delta H minus delta U sub M is equal to negative 2.77 times 10 to the 5th joules per mole. Is that a big difference? Yeah, that is a way bigger difference. So, when can you approximate that delta H and delta U are the same for liquids and gas, or excuse me, for liquids and solids? Under what conditions? Low pressure. As soon as you start cranking that pressure up, that is not the case. It changes a lot. And that's what that review there is about. If you're ever really bored and want to read about it, or want to know more about superconductors and why over in Los Alamos there's a device that literally takes 2 diamonds and squeezes stuff between 2 diamonds. Why are the scientists doing that? To get to those pressures. Yeah, and you know what? They break like a diamond, like 2 sets of diamonds every day at minimum, and they have to be like the most uniform diamonds. And what do you know about diamonds? Yeah. So always question, why are your tax dollars going out the window for these things? Okay, but what phase did we leave off? Yeah, gases. Let's talk about gases. So question. What about gases? And specifically, we know that enthalpy is equal to U plus what again? PV. There, even at ambient temperatures and pressures, volume changes change a lot. Like think about blowing up a balloon. Did I ever put a balloon in liquid nitrogen for you guys? Let's do that next time. That's fun to see. You can see the volume shrink a ton. Gases, pressure, temperature make a big impact. Let's assume an ideal gas. Where PV is equal to what? What's the equation of state? Yep. So if we look back at this expression, what could we plug in for that PV term? Yeah. Okay. We're going to ask one more question here. What would the change in enthalpy be in an isothermal experiment with the moles of gas are changing? We want to assume ideal behavior. Okay. What conditions are we not told about? What's the only condition we do know? Temperature is constant. What do we know is changing too? You know, moles of gas are changing. So, if we look at, I'm sorry, get PU plus PV plus PV, and we could plug stuff in, and we don't know what can cancel out here, right? But we do have this definition we could work off, right? H is equal to U. If we want to make these, so this is the actual value. We can't ever measure that value directly. We always have to measure changes, and we'll talk about that later on. If I wanted to make this delta H, what does U become?
Delta H.
Okay? And now this term, what's changing here?
Moles.
Moles. Is temperature changing?
No.
Is pressure changing? Maybe. Is volume changing?
We don't know.
We don't know. Maybe. It should be. We get delta nRT, where this is the change in moles of gas. Okay. So let's look at an example where we try to figure out that delta n. What is the difference between delta H sub n minus delta U sub m for the following reaction? Does anybody know what this reaction is called? I think it's titled. Yeah, it's the Haber-Bosch process. It's a very important process. Almost all of our fertilizer comes from this. The world's population would be around 1 billion right now without this process. Does anybody know what the world's population is approximately at right now? Yeah, it's like 8 billion, so 7 billion people owe their existence to this process. Actually, a significant amount of the nitrogen in all of our bodies is from this process. Okay, we have to try and calculate this thing. Let's start with let's start here. Why would we use this equation? What's,
Constant temperature.
yeah. That's the only condition we're told about. We don't know about volume, we don't know about pressure. What else do we know is changing though? Yeah, our moles, because we have a chemical reaction going on. Okay, we want to find this. What can I do here?
Subtract delta H.
Yeah. So that's pretty easy to do. We just got to find the change in moles. Okay. Delta N, it's always what minus what? Yeah. Products and reactants. Okay. Physical state's very important here. What's the only physical state we care about?
Gas.
Yeah. Gases. Because those are the ones at ambient temperature and pressure that are going to have the biggest impact to that. Okay, products. How many moles of products do we have? 2 minus. So what's our delta N? Yeah. Okay, so what we have to do now is just slug in here. 8.314 joules per mole times K. I told you what the temperature was. Math it. Look back at the solid values that we calculated at high gigapascals. Is this an appreciable number? Is it a big deal or is it not a big deal? So the gigapascals is huge. Is this a big deal at ambient temperature and pressure? Yeah, it is. You guys might not have a frame of reference for it because you got to build up more values, figure out what does that mean, but that's an appreciable amount. It's a big deal. Are there any questions about that? Yeah, Tessa.
Why are the units of that kilojoules per mole?
Oh yeah, I was bad. This technically does not have units because this is like the delta N sub M, so you'd have moles divided by moles. And this is truly unitless. I'm sorry. Good question though. Any other questions? Okay, big take-home things. Delta H is heavily impacted by pressure, volume, and so on. For gases, you can't assume enthalpy is exactly equal to change in internal energy. For solids and liquids, you might be able to get away with it, but it really depends on your conditions. Okay?